Hi everybody, my name is Dmitrii Nabok and I welcome you at my talk. As it follows from the title in this presentation, we will see how we can include and study the effects of the electron plasmon and electron magnon scattering in magnetic systems. To this end, we have chosen two powerful techniques provided by the many-body perturbation theory, the GW and the GT methods, and applied them to study the electronic band structure of the elementary ferromagnets. I will also show how these techniques can be efficiently combined together and present you our new results that evidence a range of improvements with respect to experiment over the results computed with an individual approach. As an introduction to my talk, I would like to remind you about the role of electron-electron correlation effects and how these effects expose themselves in the electronic structure, specifically in the case of ferromagnetic systems. Then I'm going to introduce the two tools of the many-body perturbation theory, the GW and GT approaches, and explain which type of electron correlations they describe. Most of you are already familiar with the most famous GW approach, therefore it requires only a short introduction. However, the second method, GT, is less known, and due to its particular importance for this work, it would require a bit longer introduction. I should also mention that it is not so straightforward to apply both techniques together. Therefore, I will introduce our approach to combine both self-energies. In the results part, all the three techniques, GW, GT, and the combined GW-TU methods will be applied to study the electronic properties of the ferromagnetic iron, cobalt, and nickel. We will see how the electron plasmon and electron magnon interactions affect the band structures, and conclude about the relative contributions from the non-spin flip and the spin flip processes. Our analysis will also include a comparison between the computed spectral functions and the recent results from the spin and angle result photoemission studies. It's a long time since the DFT has deserved a place of honor among the standard tools in the material science. I remind you that, strictly speaking, the area of application of DFT is limited by the ground state properties, and the quantum eigenvalues do not carry any physical meaning. Nevertheless, these eigenvalues are often used to characterize the single particle excitation spectrum. And as it has been shown in many studies, DFT does provide good results with respect to experimental measurements. As you can see from this figure, the local spin density approximation yields the band structure of iron in a spectacular agreement with experiment. However, if we look closer, what is actually measured in ARPES, we will see some important differences. Thus, in contrast to the DFT bands, each band in the experimental spectrum has a line width. The line width that I'm referring to has a quantum mechanical nature due to the scattering processes, and in this case has nothing to do with the experimental resolution. The line width is inversely proportional to the electronic state lifetime, and therefore has an important influence on the functionality of an electronic device. The peak positions could be extracted and compared with the DFT band energies. However, the DFT cannot clearly tell us about the lifetime effects. The ARPES studies of iron have also revealed a rather pronounced dependence of the band broadening on the spin. Moreover, the electronic bands are not just smeared out. One can also observe dispersion anomalies that look like kinks or waterfall structures in the different parts of the spectra. It is well known that such dispersion anomalies are the important indicators of the many-body scattering processes. These include, for instance, the ubiquitous electron-phonon interaction, the electron plasmon scattering, the electron magnon interaction if we consider material with magnetic moments, and many other. These processes are very complex and going far beyond the scope of the mean field theory such as DFT. As it was announced in this work, we concentrate only on the effects that arise due to the electron plasmon and electron magnon interactions. Therefore, we proceed with the discussion how the Bose scatterings could be included into ab initio framework. The many-body perturbation theory is a general and versatile method in the theoretical physics. One should always keep in mind that the green function-based techniques are not among the most computationally efficient methods. However, their power isn't different. They provide a physically transparent interaction picture and therefore are very useful to build efficient models and approximations. As an example of such modeling, we will see how different types of the electron-electron scattering events that are playing an important role in metallic ferromagnets could be included. The formal definition of a green function is given by the formula. It is also called a particle propagator, since it describes the probability that a particle induced in the state 2, the state in this case includes coordinate, time, and spin, will be found later at another state 1. Useful feature of the green function that, similar to the DFT, it contains inside the information about the ground state properties, such as the total energy, expectation values of operators, and many more. However, what's more important, the poles of the green function correspond precisely to the single particle excitation energies. By construction, the green function is a complex-valued object that does not have a direct physical meaning, which is surely not surprising if you remember, for instance, the definition of a wave function. However, it's closely related to another widely used object, the spectral function A, that is proportional to the imaginary part of the green function. In contrast to G, A is a real-valued function and has a meaning of a density of states per unit energy. The connection between two objects is given by the following integral transformation. But what's even more important, the spectral function enters into the definition of the photocurrent, the experimentally measured quantity that, for instance, could be extracted from the angle-resolved photoemission experiment. To obtain the green function, one needs to solve the quantum mechanical equation of motion. As it's shown in many textbooks, the equation of motion for the green function can be transformed into a form that bears a resemblance to the Schrödinger equation for the wave function. Formally, this equation also defines a new important object, the self-energy operator sigma, which plays a role of a generalized interaction potential. In practice, one uses the perturbation theory to solve this very complicated integral differential equation. Taking into account that we have already a very good starting point provided by the density functional theory, we can use it to define G0, the unperturbed green function. Then, by putting G0 in the equation of motion, one obtains the famous Dyson equation, which provides the solution for the interacting green functions. At this stage, it is very instructive to convert the Dyson equation for the green functions into the language of the spectral functions, which we are going to see many times in this work. The non-interacting spectral function is given as the sum of delta peaks, located at the single particle eigenstate energies epsilon. Using the Dyson equation, the spectral function matrix elements of the interacting systems are determined by this equation. Now, if we consider the frequency dependence of the interacting spectral function, we can easily understand the meaning of the self-energy. The spectral function has a form of Lorentzian, such that the real part of the self-energy is responsible for the renormalization of the independent particle energies. The imaginary part of the self-energy quantifies the peak widths and therefore the lifetime effects. Moreover, the structure of the self-energy determines many other spectral features, such as satellites, for instance. The non-shaded area describes the energy losses that show how the energy of the electron is transformed to other type of excitations. It should be additionally noted, if the interaction is strong, the quasi-particle peak can be shifted and smeared so strongly that one cannot anymore establish one-to-one correspondence between the peak in the independent and interacting pictures. In this case, one says that the state loses its quasi-particle nature. So we have an equation of motion for the green function, but the equation would still remain unsolvable until we do not specify the self-energy. The exact expression for the self-energy is clearly unknown, since it would require to solve the entire many-body problem. Therefore, similar to the situation with the exchange correlation potential in the DFT, one has to develop an approximation. The very first and at the same time the most successful in widely used approximations in many-body perturbation theory is GW, where the self-energy is given by a simple product of the green function and the screened Coulomb potential. Looking at the corresponding Feynman diagram, one can understand the essence of this approximation. A propagating particle induces a perturbation in the system of the interacting electrons such that the perturbed environment acts back on the particle via a dynamical screened Coulomb potential. One could use the following analogy to understand the process described by the GW self-energy. Let's imagine there is a sea of interacting electrons. At some moment, one drops an external particle into the water. It perturbs the sea and leads to formation of waves. The emerging waves are, in its turn, acting on the particle. The process of the mutual interaction will be continued until the system reaches an equilibrium. Remembering that the quantum mechanical analog of a wave in the sea of electrons is called plasmon, one says that GW, self-energy, describes the electron-plasmon scattering. It is important to emphasize that the GW approximation by construction does not include those processes that change the spin of electrons. What then could be a way to include the spin flip scattering into our calculations? For that, in our recent publication, we have presented an approach to incorporate the spin flip excitations by taking into account high-order diagrams in the expansion of the Hedin self-energy in terms of the screen Coulomb potential. In the figure, you can see the self-energy expanded up to the third order in W, where W is depicted with the wavy line. As you can easily recognize, the first order diagram is the GW approximation. Looking just at the shape of the diagrams of the second and the third order, one can conclude that the most of them do not include electron spin flips similar to GW. Only two types of the third order diagrams do contain the spin flip. These diagrams are indicated in the red area and describe two types of the processes involving the spin flip. First process, when a propagating particle excites an electron hole pair with opposite spins. This is exactly the process we are looking for, since it describes the Stoner excitation in magnets. The second diagram corresponds to another process, the correlated motion of a particle-particle pair. It should be mentioned that this process could also play a role, but it is expected to have a lower magnitude and be located in the energy range far from the Fermi level. Therefore, we don't consider this type of the spin flip scattering in this work. If we continue expanding the self-energy to high order, we will always find those diagrams that include the spin flip processes of the required type. All of them will have a common ladder-like shape, therefore they are called the ladder diagrams. This type of diagrams is well known and used in many fields working with the scattering processes. They are forming the basis of the T-matrix approach. It's important to note that the infinite sum of the ladder diagrams does not contain contributions that are already included into GW type of diagrams. Therefore, by construction, the combination of GW and GT diagrams is double counting free and therefore does not require any special treatment. This is one of key properties that distinguishes our formulation of the GW plus GT theory from earlier works. Being represented as the infinite sum of the special form spin flip diagrams, the GT self-energy can be computed by recasting the sum into a form of the Bethe-Salpeter equation. That is an analog of the Dyson equation, but for the two particle objects. This formulation, T object, plays a role of a magnum propagator. It is obviously a very complicated four-point equation, but the good news is that it can be solved very efficiently using the Wannier function formulation. More technical details on the numerical implementation for the GT self-energy can be found in the corresponding publication. Summarizing the theory part, I show you the final form for the self-energy that is going to be used in this work. In the diagrammatic representation, the GT ladder diagrams can be bended in the shown way to make it look similar to the GW diagram. This is very helpful because it allows us to understand better the physical meaning of the GT self-energy. The T matrix can be viewed as an effective interaction that acts through the exchange of magnons in much the same way as W includes the exchange of plasmons. Before we proceed with results, I would like to give you a summary of computational parameters important for those who would like to apply this approach in their own studies. The ground state calculations are performed using the FLEUR code, where we have used the following convergence parameters. The ground state output serves as an input for the specs code, where all GW, GT, and the combined GW plus GT techniques are efficiently implemented. It should be emphasized that due to the characteristic energy of the magnon excitations, milli-electron volts, a special care should be given to the treatment of the frequency dependency. To reach the required energy resolution, it is important to employ the contour deformation frequency integration technique with an appropriate choice for the integration grids. K-point convergence is also playing an important role, but due to the new tetrahedron integration method developed specially for the GT self-energy and implemented in specs, the convergence can be reached already for grids of a moderate size. With this, we proceed with discussion of the numerical results. We start with the results computed in the GW approach. In the figure you can see the heat map representation for the spectral functions in iron, corresponding to two spin channels. The spectral function is computed along gamma H path, for which the high-resolution ARPS data is available. The experimentally extracted quasi-particle energies are included for one of the spin-down bands in the vicinity of the dispersion anomaly. The red thin lines depict the LSDA band structure. Comparing LSDA and GW results, we see that the band structures are rather similar to each other. Nevertheless, GW still leads to some improvements over LSDA. Firstly, LSDA is known to overestimate D band width, and GW brings those values to a closer agreement to experiment. Secondly, GW provides the important information about the state lifetime. One can see that the bands are rather narrow in the vicinity of the Fermi energy and getting strongly broadened when going down in the energy. Since GW describes the electron-plasma scattering, we can conclude that this scattering process becomes important for deep line valence states. However, if you look at the dispersion anomaly, GW bands do not reveal any. The band broadening predicted in GW does not show that strong spin dependency as it's seen in the experiment. The lifetime broadening for the valence states is also found to be too low with respect to experimental values. Let's consider now what happens with the electronic band structure of iron when we include the electron-magnon scattering by replacing the GW self-energy with the GT self-energy. First, what strikes the eye, all bands are strongly broadened. The broadening gets strong already for the states lying close to the Fermi level, in contrast to GW. The broadening effects are clearly different for spin-up and spin-down states. There is a bunch of places where the dispersion anomalies are emerging. Thus, the spin-down valence band clearly shows a waterfall structure, in a nice agreement with the experiment. Moreover, we can observe an interesting band splitting in the dispersion of the unoccupied bands lying just above the Fermi level. However, there are also a few problems with the GT spectra. The band energies are lying quite off the experimental values. For some spin-up states, the band broadening seems to be extreme. So what happens if you combine both GW and GT self-energies? We obtain very noticeable improvements in the spectra. The GWT band structure comprises the best characteristics of the GW and GT results. Band energies are described definitely better than in GT, and we will see in a moment superior results of GW. Importantly, the dispersion anomalies observed in GT are mostly preserved, but the broadening has become much less extreme. The experimental kink is reproduced better in terms of the shape and the position. As a notice, even though we have a sum of two self-energies, the spectral functions are not additive. It explains the changes in intensity and broadening of the quasi-particle peaks. To support our observations even further, I'm offering to look at another path along gamma n, for which the ARPS measurements are also available. Similar to the results on the previous slide, GWT spectra again superior results obtained with the LSDA, GW, and GT alone. For instance, LSDA predicts whole pockets at n point of the Brillouin zone for both spin channels. The GW self-energy pushes this band below the Fermi level to the position that agrees well with the experiment. The GT self-energy alone does not affect this band and gives the results rather similar to LSDA. Combining GW and GT self-energies gives the band energies that are close to the GW ones, and therefore nicely agree with the experiment. Moreover, for some states, GWT predicts band dispersion in an even better agreement with experiment than GW. It is also interesting to notice that there is no experimental band energies have been extracted in the interval of energies from -2 to -1 eV in the spin majority channel. This observation seems to be nicely supported by our GWT results. The quasi-particle states are smeared so strongly in this energy region that the quasi-particle character is almost lost. Therefore, one cannot identify any clear peak. We have performed the same calculations for two other compounds in the series of the elementary ferromagnets FCC cobalt and FCC nickel. However, due to a time frame, I cannot analyze them in detail. I would like to mention only a few things. For both materials, our conclusions that GWT results comprise the base features of the individual GW and GT approaches remains unchanged. The main difference in the results with respect to iron can be easily observed for the minority spin channel, where the GW and GWT spectra look very similar. This is closely related to the higher number of d electrons in cobalt and nickel that does not provide enough phase space for the spin flip excitations. In other words, the electron-magnon coupling is smaller for the spin-down electrons. The intense broadening and dispersion anomalies induced by the electron-magnon scattering are nevertheless well pronounced in the spin-up channel of cobalt. In nickel, even though the electron-magnon coupling doesn't reveal some interesting spectral features in the GT spin-up spectrum, its contribution is too small with respect to the GW self-energy. Therefore, GW and GWT spectra are looking very similar to each other for both spins. As my final slide, since I mentioned so many times about the agreement or disagreement in terms of the band broadening, I would like to show you an example with a quantitative analysis. I remind you that according to the definition of the spectral function, the imaginary part of the self-energy determines the quasi-particle peak broadening. High-resolution RPS measurement could be not only used to extract the peak positions, but also the band widths. In this way, the computed and measured values for the imaginary part of the self-energy could be compared. The comparison is presented in the following figure for a minority band in iron. As we can see, in contrast to GW, GT and GWT results agree very well with the experimental estimates. This fact could be used to stress the important role of the electron-magnon scattering in the discussed materials. In summary, we have computed and analyzed the electronic structure of the elementary ferromagnets in the presence of both the electron plasmon and electron-magnon scattering. I have presented the results computed with a variety of techniques and discussed their strong and weak sides. I have shown you that the combined GW plus GT method outperforms the individual techniques. We saw that GWT self-energy does lead to an improved with respect to experiment description for band energies and band widths, lifetime effects, location and shape of the electron-magnon-induced dispersion anomalies. As an outlook, the presented study could be considered as a basis for applying the GWT approach to a wider class of magnetic systems. With this message, I finish my talk, and thank you for your attention.